Okay, so we've seen that dissimilar materials rub together, get charged, like the comb brushing the hair and so on. Let's look a little more deeply at this phenomenon. So the comb picks up a negative charge and the hair ends up being positive. So you have separation of charge. But doesn't that fly in the face of our famous equation, F equals ma, the one that people write country songs about? Force is supposed to dictate the direction of the acceleration and hence the motion. So the force is to the right. The electrons are being pulled to the positively charged hair. Why on earth do they move to the left then? This seems to defy this basic equation F equals ma. So let me pause over here and let you think about this for a second, and then we'll get to the answer of what's going on. So the short answer is there is no such equation in physics. It's not F equals ma, it's F net equals ma. And the electric force is not the only game in town. When I move this comb away from my hair, there's a force coming from my hand. If you remember those old problems with those inclined planes, you have a mass over here. Gravity wants to pull it down, but you could have a hand pushing this thing and make it go up the inclined plane. So you can have other forces present, and that's what's going on basically. So besides the force coming from a hand to pull the comb away from the hair, you also have valence, chemical valence, differences in electron affinity and things like that. All atoms don't have an equal affinity for the electron. This is in addition to the electric forces. So let's look at what happens in the formation of sodium chloride, for example, how you have charge transfer. And something like that happens with the comb and the hair. So in the formation of sodium chloride, sodium has 2, 8, and 1 electron in its different shells. Chlorine has 2, 8, and 7. There's a tendency to fill an orbital, the outer orbital, with 8 electrons. So sodium has just one lonely neglected electron over here. It doesn't have a particularly strong emotional bond with the sodium nucleus. On the other hand, chlorine already has 7. It's happy to adopt an extra electron. So this electron ends up going towards the chlorine. So you have a polar molecule. So even though the electric forces dictate that the sodium should stay the way it is and not lend its electron to chlorine, other forces are at play. And you have the chlorine ends up being negative, and the sodium part ends up being positive, and these are then held together by this electrostatic force. And that is the basis of an ionic bond, basically. So same thing happens on a macroscopic level. When you rub different materials together, there are different electron affinities, and just because the electric force wants everything to be neutral, that's not the winner necessarily. Other forces are at play. Another little factoid to be aware of before we go into the calculation aspects of charges and forces. That is the distinction between conductors and insulators. So some materials, like in the case of sodium, if you put a bunch of these atoms together to form a solid, these outside electrons are not particularly loyal to their own nucleus. So they end up becoming community property, so to speak. So these electrons are mobile. They can move around. They can carry a charge. This is a conductor. On the other hand, materials like plastics and so on, the electrons are more bound. They're not free to move. So this thing cannot conduct electricity. So this is an insulator. So you have this distinction. So with this out of the way, let's now look at the forces between charges in more detail. So far we viewed electric charging as just a qualitative phenomenon. Charge is a property that if you have more charge, you have more force and so on. But let's now put a number on the charge. We want to elevate the electric charge to a physical quantity. So in order to do that, we need measurements. So what is the property of a charge? It leads to a force. Therefore, the force is a measurement of the electrical charge. So we find that the more charge, the bigger the force. If you brush the hair longer, it can pull pieces of paper more strongly. If you do this in a quantitative manner, it can be shown that the force is actually proportional to the charge. Similarly, the hair itself is charged. The hair has the opposite charge. That's why the hair gets attracted to the comb. its charge also factors in. The more the hair is charged, the bigger the pull. So the force is proportional not just to the first charge, but also to the second charge over here. Then how about the distance between them? As you bring a charged object close to another one, it pulls on it. The closer it is, the stronger the force. This can be measured very easily, and it's seen that the force gets weaker as the inverse square of the distance. You have an inverse square law. So this is the third ingredient of this. So the force is proportional to the first charge, the second charge, and the inverse square of the distance. A lot like gravitation, by the way. In Newton's law of universal gravitation, you had force of gravity is equal to G m1 m2 over r squared. So it's proportional to the first mass, the second mass, and the inverse square of the distance. Very similar. So we can combine these proportionalities together, which gives you this over here. And as we did for Newton's law of gravitation, you can convert a proportionality into an equation by introducing a constant of proportionality. In Newton's case, that was G, the constant of gravitation. So here, that constant is K. This is Coulomb's constant. And this law here that makes a connection between the force, the one charge, the second charge, the distance, and plus the constant, this thing is called Coulomb's law. So it's the force law. It's like the electric version of Newton's law of universal gravitation. So this is the connection between these three things. Now what's the value of K? In a logical system of units, the units of charge should be chosen such that when you have one unit of distance and 1 unit of charge, you should get the force with K equal to 1. So there is such a system of units, but we are not going to use it. So that system of units in which K is 1 is called the Gaussian-Cgius system of unit. In that, indeed, the unit of charge, the stat coulomb, if you use that and use centimeters for distance, the force ends up being 1 with K equal to 1. However, we are using the MKSA system of units, meters, kilograms, seconds, and ampere. So the charge already had a certain value. In that system of units, the K is equal to 9 times 10 to the 9. So the 10 to the 9 value for K, it connects. If you put in meters for the distance and coulombs for the charge, you end up with the force in the proper MKSA units, which is basically a Newton. So Coulomb's law is one of the laws that governs electric charges and forces. It tells you the magnitude of the force between two charges. A second separate law is the law of conservation of charge. So this tells you that any process like brushing your hair and stuff like that, you have transfer of charge, but you have no net creation of charge. So as far as we know, the universe overall is absolutely neutral. There is no excess positive or negative charge. And in fact, even if you had a small imbalance, like 1 extra electron for every 10 to the 36 proton, that electric force could overwhelm gravity and change the overall structure of the universe, and which is not the case. So measurements of things like the cosmic microwave background, etc., would be different. So we know to a high degree of accuracy that the universe is very close to zero as far as the net charge is concerned. And this brings us to the third law in electrostatics, which is the law of superposition of electric forces. So Coulomb's law, if you have like 3 charges sitting on an equilateral triangle like this over here, then this charge Q2 would push Q2 away from it and exert a force F2 on 1. Similarly, charge Q3 would exert a force on Q1, creating this force F3 on 1 in this direction. So Coulomb's law just tells you what each of these forces is, and the direction is along the line joining the forces. It's repulsive for like signs, attractive for opposite sign. It does not tell you what to do when you have multiple electric forces present. So as it happens, these add vectorially. And the fact that they do is a gift. It should not be taken for granted. So this is a separate law. Sometimes it's called the principle of superposition and things like that. It's not a principle. It's not an assumption. It's an observed pattern of behavior. It is a fact separately from Coulomb's law. So it really is a law of superposition of the electric forces. It tells you can add them vectorially. So now let's proceed to use these laws in combination to find the net force on charge Q1 caused by Q1 and Q2. So this will be like a practical example as well in for how you do force calculations in electric situations. So here's the situation that you have. You have three charges sitting on an equilateral triangle. All of the charges have the same value. Q1 equals Q2 equals Q3. They're all 4 nanocoulomb. Then it's an equilateral triangle, so all the sides are the same. Each side is 0.5 meters. So we want to find the total force acting on Q1. So that total force, as we just said, because of the law of superposition of forces, it's equal to the vector sum of the force of 2 on charge 1 and the force of Q3 on Q1, which is force of 3 on 1. So you add these vectorially. So to do that, you need to calculate the magnitude of each force, find the x component, find the y component. You add the x component, that's going to give the x of the total. You add the y components, that's going to give the y component of the total. So the magnitude is given by Coulomb's law. Coulomb's law tells you that the force magnitude is k q1 q2 over r squared. So k is the Coulomb's constant, is 9 times 10 to the 9. Q1 is 4 nanocoulombs, as we had from before. Then the Q2, all the three charges are the same. So Q2 is also 4 nanocoulombs. So multiply them together, divide them by r squared. The distance between the different charges is half a meter. So divided by 0.5 squared. Crunch this out. This gives you the magnitude of the force. Is 5.76 10 to the minus 7 Newton. This is for both the first force and the second force. They're equal in magnitude. Now we need to figure in the direction so we can find the x and the y components. So anytime you're trying to figure out the angles and components of a vector, always move the vectors so that the tails are at the origin of the axes. So here these things are floating in the air. Move them so that the tail is at the origin. So I've done that over here. So this is that first force of charge 2 on charge 1. I just moved this force was like up here in the air. I basically just moved it down here so that the tail of the vector is at the origin. Same with the other one. That force was up here somewhere, and then I just moved it so that the tail is at the origin. Now I can figure out the angle. So once the tails of the vectors are at the origin, the angles are measured from the x-axis. This is x and this is y, by the way. You measure from the x-axis to the direction of the vector that is pointing in. So that angle is 60 degrees for this vector over here. And for the other one, again, you start at the x-axis. You go around until you get to the direction that vector is pointing in. And this whole angle here, this is 120 degrees. So that's the angle for the second vector. So now to find the x components, the force of 3 on 1, its x component is the magnitude times cosine of its angle. So this is the force of 3 on 1. It's pointing this way in the kind of northwest direction. So its angle is 120 degrees. Its magnitude we found earlier is 5.76 10 to the minus 7. So cosine of 120, that gives you the x component. Similarly for the other force, F2 on 1 over here, it's going to be the magnitude, cosine of the angle, which is 60 degrees. So cosine of 60 degrees. When you find these out, these are the values, the x components of those two forces. Notice that one is negative and one is positive. So these are going to basically cancel out. There's going to be no x component. So the x component is equal to 0. Now repeat this process for the y component. For the y component is the same thing. Instead of cosine theta, now we have a sine theta. So f of 3 on 1, the y component, is the magnitude, sine of 120. The force of 2 on 1, y component, is the magnitude, cosine of 60. This should be actually sine of 60. Sine of 60. So when you calculate these out, you get 4.99 10 to the minus 7 newtons for both of them. Both of them are positive. So the total y component of the electric forces acting from the two sides, you add them up. These are the two y components. They don't cancel. Both are positive. You end up with 9.98 10 to the minus 7 newtons. So this should be newtons. So putting this together, the total force, this is the x component, that's the y component. So this over here is F of x, and this is F of y for the total force on there. With knowing the x and the y components, you can now proceed to find the magnitude and the direction. So the magnitude is x squared plus y squared square root. For the angle is arctangent of the y over the x. So let's now proceed to do that. So here is that. So the total force, the magnitude, is equal to the x squared plus y squared square root. You square each of these. This is just 0, and you add them and take a square root. You end up with the total magnitude of the force. And then for the angle, it's arctangent of the y component over the x component. Sometimes plus 180 degrees if it's in the second or the third quadrant. So what are these quadrants? So here are the x and the y axes. This is x and this is y over here. And this is the first quadrant, second quadrant, third quadrant, and fourth quadrant. So if your angle lies in the second or the third quadrant, most calculators will give you a wrong answer for when you do the arctangent. So you have to manually add 180 degrees. So let's proceed to calculate this and look at where the angle is, and then go from there. So the next topic in this chapter is electric field. So consider the following. If I turn on an electric fan and there's a piece of paper suspended over here, the statement, the paper gets pushed away. Is this statement correct? The fan pushes the paper. So I want you to think about it for a minute, pause the video, and see what you think. So here's a little thinker question for you. So does the fan really push the piece of paper, or does the fan push the air, creating a breeze? And that breeze reaches the paper, and it's the air that's actually pushing the paper, not the fan directly. It's kind of semantics, but yes, indirectly the fan does push the piece of paper. Similarly, when you look at the force between electric charges, does one charge really push the other charge, or does it create something like a breeze that goes and attacks the other charge, creating a force? So here are the two charges, Q1 and Q2. Both are positive, so the force is repulsive. So Q2 gets pushed one way or another. The question is, do we think of Q1 as magically pushing this from a distance, or does it send out some stuff? Like the breeze that you have here, you have a breeze. Do you have something like a breeze over here, which we'll call an electric field? And it's this electric field that's created by Q1 that's causing a force on Q2. So it seems like it's just semantics, but the electric field, as it turns out, it can be detected separately, and it can have an existence even in the absence of charges. First of all, you can create an electric field without any charge, something we'll discuss a little bit later. And then another fact is, if you're looking at a star at a distance through a telescope, that star could be millions of light years away. That star may not exist right now, but you're still seeing the light. The light that's reaching your eye, it consists of electric and magnetic field. So that electric field has an existence of its own, separately from the charge that caused it. And in fact, as I mentioned, it's possible to create an electric field without any net charge. So this is the idea, that the first charge creates an electric field, like the breeze from the fan. This is what's exerting a force on Q2. So in this picture then, the force equation breaks down in the following way. So here's the situation. You have one charge exerting force on another through an intermediary agent, which is the electric field. That's like the breeze from the fan. So from Coulomb's law, that force is K Q1 Q2 over R squared. If you think of Q1 as causing this electric field, you can group kq1 over r squared together in these parentheses, and this times q2. This is the same equation. I kind of partitioned the different factors in this way. So if you view this as the electric field that's causing the force, then this whole group can be called E. So this is the electric field created by the first charge. It's kq1 q2 q1 over r squared, this blue thing over here, and that's causing the force. So the law of superposition of forces that you had, the superposition law for electric forces, it holds equally for electric field, but they're basically the basis of the electric force now. And as far as the units are concerned, so you have the equation F is equal to E times Q over here. So therefore E is F over Q. The electric field is a force per unit charge. And since force is in newtons and charge is in coulomb, the logical unit for E is newtons per coulomb. For other reasons that we'll see later, an equivalent unit for the electric field is also volts per meter, V over M.